In this section, we're going to start looking at an overview of hypothesis testing. A hypothesis test basically checks or tests a statement about a population parameter. Now remember, a population and parameter, they both start with the letter P, and so again, a parameter is a numerical value that describes a value from a population. So some parameters that we like to look at are things like mu, and remember this is the population mean. We also like to look at P, which is the population proportion. And then sometimes we'll also look at some other ones, something like sigma. The Greek letter sigma is the population standard deviation. So we're trying to check some sort of a claim or statement about one of these parameters. We might be checking something like the mean is less than 10, or the proportion is more than 50%, or the standard deviation is greater than 2. So all these are different sorts of parameters that we could be working with and checking on. Now, and what we're looking at today is an overview. We're not pulling together one entire hypothesis test in your homework problems, but I'm going to go through a couple of different examples in our notes so that way you have kind of a basic understanding of what we're working on. There's a couple of different approaches to hypothesis testing. The first one that we're going to look at is called the classical approach. Now we'll need your normal tables and a calculator for both the classical and the p-value approach. Now one thing I'd like to point out is you can use either of the approaches that I'm about to show you, but specifically my math lab will ask you questions about a particular approach, so it's important that we know both of them. So, series of steps. Now some books say there's 10 steps and others say 8 and some say 6. So depending on the textbook you're looking at, there'll be a different number of steps, but they're still all covering the same thing. The first step is to state HO and HA. Now sometimes HA is listed as H1, so just so you know, these are equivalent statements. Now HO is called the null hypothesis. It's the true state of nature, things as they are now. And then you come up with some sort of an invention or an improvement, and then you try and see if there's been a change over the way they are now. And that's your alternative hypothesis. Now remember, an alternative hypothesis can also be denoted H1. So you'll see these used interchangeably. And this is the researcher's claim. This is the new claim. And we're going to get into a lot more detail with this a little bit further down. But for now, I just kind of want to look at an overview of what's happening here. The second step is to state the level of significance. Now the level of significance is the Greek letter alpha. This is basically looking at how much I'm willing to be wrong. So for instance, if I talk about a 90% confidence interval like we did in the last section, I was willing to be wrong about 10% of the time. So our level of significance, or our alpha level, is basically stating, you know, how much you're willing to be wrong. Some common levels are 0.10, 0.05, and 0.01. Now there's others. In fact, there's an infinite number of significant levels of significance, but these are some pretty common ones that we'll be using. The next step is, after I find the level of significance, I will determine the critical value based on this level of significance. Now remember, the level of significance, we used alpha. And you're already good at finding critical values from when we were working with confidence intervals. Sometimes the critical values might change in hypothesis testing for different cases, but the same approach is similar to what we did in hypothesis testing. So we determine the critical value, and then we will calculate the test statistic. Now, to calculate the test statistic part, the test statistic will change based on what we're testing. So for instance, if I'm testing something about the mean, my test statistic will change than if I'm testing something about the population proportion. So there's many different test statistics, and we'll go through some examples. After you calculate the test statistic, you draw a conclusion or make a decision. Now there's only one of two decisions that you can make. One is to reject our null hypothesis, which is HO, in favor of HA, our alternative hypothesis. And the other option is to fail to reject HO, meaning there hasn't been enough evidence yet to get rid of the null hypothesis. So we fail to reject HO. Now, we don't write out fail to reject usually. We usually just use FTR, fail to reject HO. Now, after I make a decision or draw a conclusion, just saying reject HO or fail to reject HO, that's really not good enough. I need to do my last step here. And this last step is to summarize your results. Now, when we talk about summarizing your results, what we want to have done here then is we want to have some sort of a statement in terms of the problem. We don't want to just say reject HO. We want to know what the question was. We want to try and solve or draw a conclusion based on that. So you summarize your results in terms of HA and in terms of the problem. And the summarizing your results always starts the same way. We start this with the data supports the conclusion. And then we'd fill in the blanks here, or the data does not support the conclusion. So if we're trying to, again, go back up here to reject HO in favor of HA or fail to reject HO, the data supports the conclusion that this is what we would use if we were to reject HO in favor of HA. This one down here, the data does not support the conclusion. This is what I would use if I were to fail to reject HO. So this is fail to reject HO. This is reject HO. And these will make more sense once we actually do some work here in terms of an actual problem. So these are the steps that we have for the classical approach to hypothesis testing. There's another approach to hypothesis testing as well, and it's called the p-value approach. Now the p-value approach is nice because it kind of gives us an idea of how close we were to rejecting or failing to reject. It kind of gives me an idea of I was really, really close to rejecting or I was really, really far away from rejecting. Now a lot of the steps are the same. So first step is state HO and HA. And remember HA and H1 are interchangeable. The second is we will state our level of significance. And remember, our level of significance is alpha. It's kind of an error. How much are we willing to be wrong? Then what we do here is, this is kind of where they start to differ. We calculate the test statistic. And then after we calculate the test statistic, we calculate the p-value based on the test statistic. Now once we find the test statistic and I calculate the p-value, I'm going to make a decision. I have the same two decisions I can make. I can reject HO, or I can fail to reject HO. Now, one of the things we didn't talk about above is how do I make this decision? Well, we can go up and take some additional notes here in a second. For the p-value, it's easier to say though. So we would reject HO in favor of HA if my p-value was less than or equal to my level of significance alpha. We would fail to reject HO if my p-value was greater than alpha, my level of significance. So these are the two big rules for the p-value approach. And our last step would be the same as above. We would summarize your results in terms of HA. Now when we talk about this, and we need to consider summarizing our results in terms of a problem. And these will make more sense when we actually start working some of these problems. Now, same thing here. We always state this the same way. The data supports the conclusion is how we start. So the data supports the conclusion. That, and this is how we start when we reject HO. Now, if we fail to reject HO, we always start our summary as the data does not support the conclusion. Now again, this is when we fail to reject HO. Because remember, this is written in terms of the alternative. So if I reject HO, what I'm saying is that the data is tending to support the alternative hypothesis. We can never say we accept the null, or sorry, we can never say we reject the null hypothesis. Only when we reject the null hypothesis, we're implying that we have support for the alternative hypothesis. You can never say accept HA. You always talk about things in terms of the null hypothesis because that's kind of the standard of what's known. So what we have here so far is a general overview of these types of problems. Now let's flip back up. Here we talked about our rules for rejection and making a decision. Let's go ahead and add some rules back in over here when we talk about reject or fail to reject. In the classical approach, we would reject HO in favor of HA if our critical value, and remember our critical value is up here, and our test statistic are compared. So we would reject HO in favor of HA if the test statistic is more extreme than the critical value. And I'm going to use CV to represent critical value. Now, fail to reject would just be the opposite then if the test statistic is not more extreme. And again, CV is critical value here. Okay? So the only thing that this is telling me is I'm more or less. Down here, the p-value gives me an idea of how close I was because I actually can calculate this value p to compare to alpha. But again, these don't make a lot of sense until we start working some problems. Okay, the next thing I'd like to do is to kind of break up each of these steps. The first one that I want to talk about is our null and our alternative hypothesis. So I want to talk about HO and HA. Now remember, HA and H1 are the same thing. So for the null and the alternative hypothesis, you always write the null first. The null is the status quo like we said above. It's kind kind of the industry standard. It's what we think we already know. Okay, now when we state HO, it's always in terms of a parameter equal to some value. And now the value that I'm talking about is a number. Okay? So we're looking for a specific number. So some examples for some null hypotheses then would be something like mu, our population mean, equals 12. Another example could be HO, population proportion equals 56. Another example would be my null hypothesis, my population standard deviation is less than 1. So these are all examples of a null hypothesis. Now the HA, the alternative hypothesis, is called the experimenter's hypothesis. And what we do then as an experimenter, something we're trying to figure out, we say, well, I believe it's different from what we already think we know. So again, this is the experimenter's hypothesis. This is the experimenter's claim. So some different things that we could see here for HA then are something like, instead of mu equals 12, we could have mu not equal to 12. We could have something like our alternative hypothesis P is greater than 0.56. Or an alternative hypothesis where the sample standard deviation is less than 1. Oops, I have a mistake up here. This should be an equal sign. The less than case is below. The null hypothesis always has an equal sign in it. Now, not equal to means it could be larger and it could be smaller. So this is called a two-tailed test. This one, where I have the greater than case, is a one-tailed test. This is to the right, so this is called a right-tailed test. Less than case, I'm looking for numbers less than or to the left. This is called a left-tailed test. So when you write a null and an alternative hypothesis, typically they're written together. So for instance, I might have something like HO, population proportion equals 0.29 versus the alternative, this is VS meaning versus, you usually have all of these, P where I think that my population proportion is actually less than 0.29. So that would be an example of how you'd write the hypotheses together. Let's look at some other examples, HO versus HA. Here we could have a claim that the population mean for, let's say, the lifetime of some batteries is 1,200 hours. And let's say you think that you've improved on the length of life of the battery and you are testing to see if it's more than 1,200 hours. Let's look at another example, HO versus HA. Population standard deviation. We think it has quite a bit of variability, let's say 89 in terms of my battery life. We think that the process that we've come up with has decreased the variability so I have a more consistent battery, so I think it's going to be less than 89. And what ends up happening here then is I run an experiment, and after I run the experiment, then I analyze my data and I infer something about the population based on that data. Now my next step is to state the level of significance for both of the approaches. Now the level of significance is alpha. Now basically, when we're talking about stating the level of significance, we're looking at the probability of making a mistake, and we want that probability to be very, very small. So some common alphas are alphas like 0.10 that we mentioned, 0.05, and 0.01. Now there's an infinite number of possibilities here for alpha, but this gives you a pretty good idea. Now we talked about alpha as the probability of being incorrect, but it's very specific. Alpha is the probability of a type 1 error. Okay, so this is how we write that, probability of a type 1 error. This is the error that we make when we reject HO when HO is actually true. So we want that probability to be very, very small. Now our other type of error is called a beta error. Now the deal with the alpha and the beta error is we can't control them both. If we control alpha, beta kind of roams, and if we control beta, alpha roams. And it turns out that alpha is the least of the two errors in terms of consequence. So beta is the probability of a type 2 error. This is when we fail to reject HO when HO is false. So notice everything that I've written here is in terms of HO. None of it is in terms of HA. Because I don't know about HA, I'm experimenting about it, whereas HO is kind of the industry standard, the status quo that everything in your industry has been built on. Now the two approaches kind of diverge right here for a little bit, but basically what we need to do next is we need to find the critical value if we're using the classical approach. And we abbreviate critical value CV, and this is the classical approach. Okay, so when we talk about finding the critical value, we basically need to know a couple of different things. We need to know if this is a two-tail test, left tail test, or right tail test. So we need to know which of these it is. And the second thing we need to know is the level of significance, or alpha. Now we're going to assume we're working with the normal distribution right now. That's not always going to be the case, but for these examples we'll assume the normal distribution is in use. So let's look at an example for each one of these cases. So let's look at the case where we have a two-tail test and our alpha level is equal to 0.10. So what helps to know is we sketch out our normal distribution. If I'm using a two-tail test, and basically what ends up happening here with the two-tail test, I have Z is distributed normal, or approximately normal 0, 1. So my mean is at 0. And because I have a two-tail test, I'm willing to have error at the top and error at the bottom. If I have 10% error, I have to distribute it evenly between the tails, so I'd have 0.05 in either tail. Now I don't really care about the fact that there's 0.90 in here in between, but I can note that if you want to. Next thing we do is we go ahead and open up our normal tables, and I'm going to look on my normal tables where I have 0.05 to the left, and that's going to be my critical value. So let's go ahead and look at 0.05 to the left, and here's that 0.05 is exactly in between these two values, 1.64 and 1.65, and they tell us to come down here and use the value of 1.645 for my z-score. So that means I have a negative 1.645 and a positive 1.645. So these are my critical values. Plus or minus 1.645. Now, what the rule is then, if my test statistic is more extreme than plus or minus 1.645, that means I'm more than 1.645 standard deviations from the mean, we would reject HO in favor of HA. Okay, so that's the decision I would make here. So if I had a critical value that fell in this shaded region, or sorry, if I had a test statistic that fell in this shaded region, I would reject. So this is also my rejection region. And because I have a two-tail test, I can reject if I'm more extreme than 1.645, and I can also reject if I'm more extreme than negative 1.645. So this is my rejection region. This is my fail to reject region. So if I get a test statistic that falls here, I would fail to reject. So that's what I do with a two-tailed test. Okay, let's look at an example where I have a right-tailed test. And in this case, let's go ahead and use an alpha level of 0.01. And again, we're assuming we're using a normal distribution, mean is 0, standard deviation of 1. Now because this is a right tail test, all my error is up here in the right tail. So this is 0.01. This is my rejection region. This is where I would reject HO. And over here was my failed to reject HO, FTR, failed to reject HO. Okay, now in order to find this 0.01, there's several things I can do. If I look on my normal tables, I could use symmetry, and I could look up 0.01 on the left-hand side, and let's get as close as we can here. 0.01. We're getting closer here. So the closest I think I can get to 0.01 is right here at 2.33, so negative 2.33. And then because of symmetry, I know that this value is a positive 2.33. Now, also because my area under the curve is always equal to 1, if I have 0.01 in the upper right tail, that means I have 0.99 in the lower tail. So I could look up 0.99 on the left, and I'd get 2.33 as well. Now you can use the inverse normal function on your calculators to find these as well. So for inverse normal function, let's make sure we have our picture here. I would do second DISTR, inverse normal. The area to the left would be 0.99 like we talked about. If 1% is in this shaded region, 0.99 is in the non-shaded region. My mean is 0 and my standard deviation is 1. And so you can see we get this value of 2.33 if we round to 2 places. So my critical value then, I only have 1 because I only have one tail. My critical value is 2.33. So then my decision would be if my test statistic is more than 2.33, I would reject HO in favor of HA. Okay, so now up here I said more extreme, because that took into account both tails. More extreme than 1.645, more extreme than negative 1.645. But here I can just say more than because it's only a single tail test. Okay, let's go ahead and look at the left tail test. So for my left tail test here, let's use alpha equals 0.05, and we're assuming that we have our standard normal distribution. So we go ahead and draw our quick curve. Now if I have a left tail test, that tells me that my error is all distributed in the left tail. So this is my rejection region. This is my fail to reject region. And again, my mean is here at 0. So in order for me to find this value, we're going to pop into the normal tables, or we can use our inverse normal. So let's look at inverse normal. Now here, the area to the left would be 0.05. My mean is 0 and my standard deviation is 1. And I get negative 1.645. Now this is that weird case where we actually go out to an extra place. And I'll show you this on our normal tables. So if I look up 0.05 in my normal tables, you can see I'm exactly in between these two values. Whoops, that's not right. I'm exactly in between these two values, so that's when I use that 1.645. Now we have to be careful here. I also used the same value when I had 10% error, but that's when it was split between two tails. This is just a single tail, so that's why it's different. So my critical value is negative 1.645. So my decision would be if my test statistic is less than negative 1.645, I would reject HO in favor of HA. Now, if it's not the case, I'd fail to reject. So this is an example of all my different null and alternative hypotheses, two-tail, right tail, left tail. And then these are also examples then of how we would work with making a decision based on those. Now, this is the classical approach to hypothesis testing. Now, no matter what approach we use, the next step would be to calculate the test statistic. Now, there's several different test statistics depending on the situation that we have. So one test statistic, if we were checking the population proportion, would be Z equals P hat. Remember, this is my estimate, P hat minus P. This comes from my null hypothesis, all over P hat Q hat over N square rooted. P hat Q hat over N. The square root goes to PQNN. So there's an example of a test statistic. Now again, there's several different test statistics that we're going to be using. For this particular homework, I think the only one that they ask you to use is this test statistic. In other sections, we'll be learning more test statistics. So this is ours that we're going to be using for now. And remember, Z is distributed normal 0, 1. P hat is my statistic, it's my population, or sorry, my sample statistic. So this is my sample proportion. A lot of times we can say it's calculated X over N or given. Sometimes it's given as 15% or something like that. P is my population proportion. The population proportion comes from HO. It will be given to you somehow. We assume a proportion, and then we're going to do some sort of an experiment and see if the proportion changes. And of course, N is my sample size. Now, once you calculate the test statistic, if you're using the classical approach, I come up here and I look at these three cases, and I decide whether or not I can reject HO. And then if I'm using the p-value approach, the next thing I'll do is to calculate the p-value. Now there's two things I need to know to calculate the p-value. First thing I need to know, is this a two-tail? And again, this is after the hypothesis. I'm trying to figure this out. Is this a two-tail, a left tail, or a right tail test? And the second thing I need to know is this test statistic that I just calculated up here. So let's look at a few examples. So for our first example, let's go ahead and suppose our test statistic is Z equal 1.23, and let's say my hypothesis test is, let's go two-tailed. Okay, so what the p-value is, it's the probability of seeing a test statistic as extreme or more extreme than the one that we see, assuming HO is true. And I'll write out a definition of that here in a second. So again, we're assuming normality. I'm using a Z, so that's standard normal distribution. Here's 1.23. So as extreme or more extreme. So this is what I'm looking at. Now because this is a two-tail, basically what I'm looking at then is when I find my area here, this is going to be half of my p-value. So what we can do, we can look up at our normal tables, and from our normal tables we could look up either positive 1.23 or negative, it doesn't matter which one because of symmetry. Here's 1.23.8907. So this area right here is 0.8907. Well, because my total area underneath my curve is 1, this is going to be 1 minus 0.8907. So let's see what that value would be when we subtract 1 minus 0.8907. So that's 0.1093. So that's this area right here. So my p-value, because this is a two-sided test, is 2 times 0.1093. So p is equal to 2 times 0.1093. So that's 0.2186. So this is my p-value. And again, this is because this was a two-tailed test. So we have to be pretty careful about how we find these values. We can use our tables, our inverse normal tables, or sorry, our normal tables as well as our calculator. So for our calculator, we'd go second DISTR, we'd look up normal CDF, and then our lower would be negative infinity, or close to like negative 100,000. My upper would be this 1.23. My mean is 0 and my standard deviation is 1. And it's going to give me this area of this 0.8907 that we see here. And so I could subtract that. Another thing I could do for this problem is I could do second DISTR, normal CDF, and I could start at 1.23 for my left, and then for my upper I could go just with a really large number like 100,000. And again, mean is 0, standard deviation is 1. And then it gives me this value directly, 0.1093. Okay, so you could also use your calculator for those. So that's an example of how to use your p-values when we're trying to figure out a two-tailed test. Okay, let's go ahead and look at another example. So let's suppose we have a test statistic. And my test statistic here is negative 2.34. And our hypothesis test is going to be a single tail test. And in this case, let's go ahead and say it's a left tail test. Okay, so what we'll do to get started is we'll sketch a quick picture. Mean is 0. Here's negative 2.34. Now because it's the left tail, we're going to shade in the area to the left. So this is my p-value right here. I don't have to double it because it's only a single tail. So if I want to find this area, I could go to my normal tables and look up negative 2.34. So here's negative 2.34 is 0.0096. So this is 0.0096. Okay, so my p-value here is equal to 0.0096. And that's if I have a left tail test. Now for the left tail test, I always sketch the area to the left. Now along the same lines, if I have a right tail test, I always sketch the area to the right for my p-value. So suppose I have a test statistic here. And for this one, let's let my z-value equal negative 0.89. And my hypothesis test would be a right tail. Now because this is a right tail test, that means I shade the area to the right. Now this one's going to seem strange to shade to the right because it takes up a large portion of our curve. So even though it's not a little small tail area, it's this larger area, it's still the area to the right. So this is going to be representative of my p-value. This is a single tail test, so I don't double. So a couple different things I could do here. I could go with my normal tables, and I could look up 0.89. So here's 0.8, and it's negative 0.89. 0.1867 would be this area. And so then my area to the right then would be 1 minus 0.1867, and that would be my p-value then. So let's look at 1 minus 0.1867. So I get 0.8133. That's a huge p-value. So my p-value for this case equals 0.8133. Okay, so we've talked about the p-values. We've talked about how we're going to make decisions now on the p-value approach and the classical approach. But one thing we haven't done is we haven't defined the p-value. But now that we see what one looks like, this might be a good place to do it. So the p-value. The p-value is the probability of seeing a value as extreme or more extreme than the test statistic. And this is the important part, assuming HO is true. So if I'm assuming HO is true, the probability of seeing an extreme value we would think would be very, very small. So small p-values provide evidence against HO. Higher p-values provide evidence for HO. Now that line where we cross has to do with the comparison of alpha. Now some of the problems that we're going to be running into ask us to make some sort of a decision. So remember, with our decision, there's only two decisions I can make. I can reject HO, or I can fail to reject HO. Now, if I reject HO, I'll do this if p is less than or equal to alpha using the p-value approach. Or if I'm using the classical approach, I will reject HO if my test statistic and my critical value compare in a certain way. So if my test statistic is greater than or equal to my critical value, or if my test statistic is less than or equal to my critical value, or if my test statistic is more extreme than the critical value. Now what are our cases here? This is the two-tail test. This is a left tail and this is a right tail. So this is right tail, left tail, and two-tail test. Now I will fail to reject HO if p is greater than alpha, or using my other approach, if the test statistic is not more extreme than the critical value. And that could go with the two-tail test, or I could say the test statistic. And you really have to be careful with this one. I guess I wouldn't write out all the cases here. We just need to remember if it's not more extreme for the fail to reject. It means none of these cases came true up here. Now once I have my decision, I need to draw my conclusion. And my conclusion is always written in terms of the alternative hypothesis. So we've written this a few times now. Summarize the results in terms of HA and in terms of the problem. Now we always start the conclusion the same way. We say the data supports the conclusion that, and then we go ahead and talk about our conclusion. And this is how we start this if we reject HO. Or we say the data does not support the conclusion and this is how we start it if we fail to reject HO. And it doesn't matter which method we use, this is how we work. Okay, so this is a good way to get started with this huge overview, and now let's look at a few quick problems. Oh, and something just popped into my head. Let's go ahead and look back at our test statistic here. Okay, the test statistic, I have a mistake on. This is p hat minus p, that's correct. But down here, what we do is we assume the null is true. So let's use PQ over N down here. So again, that's a typo that I have. This is PQ over N. Now P is given, like I have over here in the population proportion, is given in HO. So it's PQ over N. Okay, so for our first example, where we actually get to do some problems now, let's go ahead and say we want to test the hypothesis that the mean weight of mice that drink cola is, let's say, 22 grams. Okay, so what we want to do here then is we want to state HO versus our alternative HA. Now when we're talking about these, the equal to case, and we're talking about mean weight, so that's mu, is equal to 22 grams. Well, if we're testing to see if this is true, the alternative would be that it's not equal to 22 grams. So this is an example of a two-tailed test. Let's go ahead and look at another example. Now for this example, we could be talking about not necessarily the population mean, but we could be talking about the standard deviation. Let's go ahead and up here, where we have the mean weight of mice, let's test the hypothesis that the standard deviation of the weight of mice is less than 1.2 grams. So I'll set up my null in our alternative hypothesis. So I'm testing standard deviation, so that's going to go here. The equal to case is always the null. The alternative is what I'm trying to establish, less than 1.2 grams. Okay, so this is an example of where I use the left tail, a single tail test. For this next example, we're actually going to be finding a p-value, and then based on the p-value, we'll be going to make a decision. So for here, let's go ahead and determine the p-value. And make a decision. So when I talk about making a decision here, I need to talk about whether I reject or fail to reject HO. So the information I'm given is Z equals, let's do 1.24, and we have a two-tailed test, and I'm also given a level of significance of alpha equals, let's go ahead and do 0.10. So the first thing we do for the p-value is we make a quick sketch. Because we're using a z-score, we know our mean is 0, 1.24. Now this is a two-tailed test, so I need to remember to double my p-value. So I'm going to go more extreme than 1.24, and this is half of my p-value. So if I wanted to, I could look up 1.24 on my table. It's going to give me the area to the left. The easier thing to do is to look up negative 1.24 and double it, and because of symmetry I can do that. Or I can use second DISTR, normal CDF. My lower will be positive 1.24. 100,000 would be an extreme upper value. It's actually going toward infinity. My mean is 0, my standard deviation is 1. And it's giving me a value of 0.1075. So 0.1075. Now remember, this is half of p. So p is going to be 2 times 0.1075. So let's go ahead and grab our calculators and see what that's going to be equal to. So 2 times 0.1075. So I get 0.215 for my p-value. This is a big p-value. So now I'd have to make a decision. Now remember, my decision will be p less than or equal to alpha. I'm going to reject HO. And for p greater than alpha, I will fail to reject HO. So my value for alpha is 0.10. So my p-value is much larger than that. So my p-value is 0.215. It's definitely greater than 0.10, so I'd fail to reject HO. Now when we start drawing conclusions and then summarizing our results in the next section, that's when we'll go ahead and start saying some things like the data supports or the data doesn't support the conclusion that, etc. The last type of problem that you'll see in this homework set has to do with type 1 and type 2 error. So let's go ahead and find the type 1 and type 2 error for this particular null and alternative hypothesis. Let's suppose the percentage of households that have cable TV is less than 65%. So our null hypothesis and our alternative hypothesis is the first thing we want to set up. So again, equality is always going to be at my null hypothesis, but this is a percentage, so this is a proportion. So this would be where the proportion is equal to 0.65. 65% is 0.65 as a decimal. I'm looking at the less than case, so this would be p less than 0.65. So again, I'm looking at the types of error. So let's go ahead and look at type 1 error. Now remember, this is alpha. This is basically the probability of rejecting HO when HO is true. So if we were to reject HO, what we're saying here is we have support that the actual proportion is less than 65%. So when we talk about failing to reject or rejecting the null hypothesis, what we want to do then is we say we reject the null hypothesis, or we'd start with the word reject. So we'd say we reject the null hypothesis that the percentage of households with cable is 65%. So again, reject the null hypothesis that the percentage of household with cable is 65%, so that's this piece, when the percentage of households is actually equal to 65%. So we said we rejected HO, and we said, okay, we don't think that the percentage of households with cable is 65% anymore. We think it's actually less than 65%, when actually it is 65%. So a consequence of this might be something like you're on the marketing team for a cable company, and so we run this quick test to find out the percentage of households that have cable, and we're assuming, or we're trying to test to see if the percentage is less than 65%. And we find out, and we reject this, and we assume it's less than 65 when it actually is 65. So what ends up happening is we might change our marketing plans or change who we're marketing toward to gain more market share. So that's an example of a type 1 error. Let's go ahead and look at a type 2 error. Type 2 error is our beta error, and this is when we fail to reject HO when HO is false. Okay, so let's go ahead and write out what this would look like. So we would fail to reject the null hypothesis that the percentage of households with cable is 65%. So that's our first part, fail to reject, when the percentage of households with cable is actually less than 65%. So these are sometimes a bit of a tongue twister, but this is an example. We decided that HO was true. We had support for it when actually it was false, and so we decided that the percentage of people who have cable is 65% when actually it was less than 65%. So that's another way to say the same thing. So this section I know was really long, but it actually sets us up to do the next section a lot shorter because we had to go through a lot of background information. As usual, if you have any questions, you can stop by my office, you can go to the Math Center, you can also bring your questions to class, and we'd be happy to help. Good luck.